All right. Good evening, everyone. Welcome back. Welcome back to our distinguished lecture series at the International Space University Space Studies Program 2022. So here, greetings to everyone who is joining us here in the auditorium at the ISD Tagush Park Auditorium. And greetings, good morning, good afternoon, good evening to wherever you are watching us online on the ISU YouTube channel. So this week we have three evening events, three public events, let me call them. And this particular one is indeed a very, very timely one that we already advertised it last week on Tuesday when we saw the spectacular images from the James Webb Space Telescope. It was just 6 days ago, and such a timely, distinguished lecture this is, that we will be actually hearing the story of these images, but of course much more than that, what actually will James Webb will bring in the, years, decades to come to us, and what we will actually observe and get mesmerized for it. So today we have a very special guest. Dr. Aaron Young is joining us from NASA Goddard Space Flight Center. Dr. Young's research focuses on developing physical models for galaxy formation and cosmic reionization using semi-analytical modeling techniques. Also investigating the interplay among galaxies, supermassive black holes, and the cosmic environment in the earliest episodes of our universe's evolution history. He obviously works closely with the observation teams on providing the theory support for the upcoming James Webb Space Telescope observing programs based on his simulation work, semi-analytical forecast for the James Webb Space Telescopes. So thank you very much for joining us, and give him a very warm applause. Welcome, please. Thank you.
Can we have the lights turned down a little bit? Because I don't think we can see galaxies with this light. Just like in the real universe, real world, we need to be able to go a little dimmer before we can see galaxies. So thank you for the warm introduction. Thank you, ISU and Jim Green, for inviting me to give a talk here. It's really exciting to give this talk in this group because the images just came out 6 days ago. I'm sure you have all seen it. So why am I even here? I'm just kidding. So for those of you who care, you probably have seen it already. And for those of you who didn't care, I need to make sure you care about it. So this is my job here. All right, so before I start, let me just tell you a little bit about my day job, which was actually already done in the introduction. So I'm a theoretical astrophysicist, so I don't actually know how to use James Webb. I'm also not involved in making James Webb happen, but I create simulations of the universe. I simulate how galaxies form since the Big Bang. So if you're interested in that kind of thing, I'll be around throughout the rest of the week, and I'm happy to talk about that work with you. And maybe in the future, I can also come back here and teach you how to simulate a piece of the universe. But that's what I do as a day job. I support observing teams. I tell them what they can see in the universe before James Webb is even launched. So, and hopefully they are correct. But if not, we'll learn a lot from them. We'll learn how the universe works and learn a lot of physics out of it. But let's jump right in. So this is where I want to start because I saw today in my badge, it says citizen of planet Earth. So this is where we live, this is where we are. And a view like this just reminds me of, there's always a camera floating up there. That's how we take an image like this, of course. But also, there are satellites up there that, you guys put up there. And also a space station that was, operating up there, representing our constant human presence in orbit for the past 2 decades. This is our habitat. So this is where we live. Now the question is, where else have we been? So that's the moon. For us, at least in the Apollo era, it took a little over 3 days for us to get there. And a text message from the moon would take a second to get back to us. This is like our backyard. We have been there. We left footprints on there. We left a bunch of things in there. There are things that we know they're there. There are things that we cannot find. I learned a lot of those from Jim. But the moon, we have been to the moon. Where else have we been? So, there's a lag, but this is the inner solar system, and we have obviously been to the Mars, planet Mars, right next door. So Mars is a little trickier. We probably know better than me. It took Perseverance about 7 months to get there, and from Mars, a text message will get 11 minutes to get back to us. But things get trickier because it moves around, so we get to launch things every 2 years. But we have been to Mars. We have been to Mars so many times that we have lander, rovers, orbiters all over the place. We have studied Mars. So we technically have been to Mars, which is great. Where else have we been? This is the rest of the solar system, not to scale, but I just want to highlight that we have been to places. We have fly all over the solar system. We have, the Parker Solar Probe that went to the sun. We have Da Vinci and Veritas scheduled to go to Venus. We also have DART, which is going to hit an asteroid in just 2 months. And then we have Lucy on the way to Jupiter. And of course, Juno is already orbiting Jupiter. And then, I know I've probably missed your favorite, but we have to talk about the king and the queen of this exploration, this flyby mission, Voyager 1 and 2. They've been flying for the past 45 years, and we've just recently left the heliopause and entered interstellar space. So it has left our sun, it's on the way out there in the space between stars. And for that distance, a message from Voyager would take about 20 hours to get to us, give or take. So 20 light hours away, which is very, very far away. And here comes the closest star. This is Proxima Centauri. Just 4 light years away, in the cosmic scale. This is practically no distance. We're right next to it. It would take like 4 years to get there. And I did, what a physicist would do, a naive back of envelope calculation. If you just divide by how quickly the Voyagers go in space and then multiply that by the distance of how long it takes, maybe it would take a couple 100,000 years, which is it's still doable. It can still send something out there in that direction, and then we'll still hit the star at some point. So it's still doable. But I want to show you too this galaxy that is next door. So we live inside a galaxy, just in case you don't know that. We live next to a star, and there are a bunch of stars in our neighborhood, and this form a galaxy. And then this is not our galaxy. This is our neighboring galaxy. So this is Andromeda Galaxy that is not too far away, in the cosmic scale of things, just 2.5 million light years. So they would take light 2.5 million years to get there. If we try to send a probe on that direction, I don't know if that will reach there before the universe ends. So maybe we have to be innovative. But that doesn't stop us from studying the planets. Well, I have to mention this. This telescope is there for 2 slides already, actually. So the only way we can study these objects, we can study the rest of the universe, is through telescopes. And this is a demonstration for how, in the past, we used Hubble to study this nearby galaxy, our dear neighbor. Let me dim things a little bit for you. So this is the part where Hubble has imaged. I know you're not here for Hubble images, but I will get there. So not even the entire galaxy, because Andromeda is huge, even though it looks small in the sky. But that is the part that Hubble imaged, and it takes several thousand, I think more than thousands of mosaics to cover this big patch of the sky. And I want to bring out the first theme of today's talk. When you get an image like this, it's shown to you on TV, go to whatever agency that released it. Go to NASA, go to ESA, grab the original image. They might be big, maybe 10, 30, 50 megabytes. Grab it and zoom in as much as possible. I know, individual stars. We can see individual stars in that galaxy. That's why, it took so many mosaics. That's why it needs Hubble to look at it, because we're imaging the galaxy at extremely high resolution. This is great to look at, but it also helps us understand how galaxies form and how, all sorts of astrophysics, like, all sorts of things. We get there. All right, so that's just one example. And here's my favorite, actually. This is the Cosmic Vista. It's called the Hubble Ultra Deep Field. In this tiny little patch of the sky, there are about 10,000 galaxies in there. 10,000, and they're all over the place in terms of distances. They are ranging from nearby a couple billion light years away, just nearby, to 13 billion light years away. So this is almost going to the edge of the universe, almost. And I said this is for a very small patch of the sky. How small is it? Well, I put the moon in there for scale. Did you see the moon? Glad you asked. Where's the moon? Well, you're going to wait maybe a second or something for it to show up. Oh, that's the moon. That's the moon. And where's the Hubble Ultra Deep Field? So those areas carved out by white lines are different patches of surveys that astronomers did in the past that we try to go deeper and deeper. Patches of the skies that we understand quite well because we observe them over and over again with multiple instruments. So there are several there. We call it wedding cake. But that's Hubble Ultra Deep Field. That thing. So that little patch of the sky contains 10,000 galaxies. And that's not all of it, because all we have is Hubble for now. So we will find more galaxies in that patch of the sky with James Webb. We're just not there yet. Maybe, by the end of the year. We got a program for that. Okay, let's zoom back in, because zooming is the theme for today's talk. Here is the Hubble Ultra Deep Field again, the whole thing, and then we zoom into it. All right, galaxies, a lot of galaxies in there. We realize that galaxies take all sorts of forms, shapes. They have different colors, they have different morphologies, they have different compositions, they have different sizes, mass, luminosity, color. Did I say color already? Yes, I did. But with this is really important. This gives us a variety, a population of galaxies to study, and through them we can understand how the universe operates. There's so many things we can extract from galaxies. Especially the universe is full of stuff, but most of that stuff we cannot see. For example, dark matter is everywhere, but we cannot see them. But these are like the tip of the iceberg. So we know when dark matter concentrate, normal matter also concentrate and galaxy forms. So when we study galaxy, we're also studying kind of the rest of the universe using them as a tracer. All right, I know that's fun to look at. Go grab the image and zoom in as much as possible. Do that. People get PhDs for doing that. Like, seriously. Anyway, so this is another fun thing to do. So let's fly through the field, because I told you these galaxies are at different distances. So astronomers spend years understanding these galaxies one by one at a time, so we can figure out exactly how far they are. And now we can put it into this kind of animation, so we can fly through it as if we can travel faster than the speed of light. And you can see that, yes, indeed, that field that looks flat to you is an amazing wedge of the universe. It's full of galaxies. There are a lot of things that we can study. And because light travels at a finite speed, so the further out we look, the further back in time we look. Like if the galaxy was from 13 billion light years away, that means the light has traveled 13 billion years. By the time it gets to us, hit the telescope, we're looking at the universe as it was 13 billion years ago. That was fun. So we have a time machine, actually. All right, are you done? That's just so cool to look at. Anyway, so what we're trying to do, I guess one of the many things we try to do is trying to create a flip book of galaxies over time. So we study populations and populations of galaxies, and by sorting out from far to close where they are, what they are, by studying that population by population, we can get a sense of how the universe evolved. There's so many things we can extract from these. For example, how did the first generation of galaxies form? What conditions are they? How big are they? How bright are they? That tell us how much stellar mass how much stellar mass is in there. And then by going forward, we try to also understand how quickly does galaxy merge? How do they get their masses? What happens after they merge? What would that do to their morphologies? How do they grow their spiral arms? Or do they become more compact over time? There's so many things going on in galaxies. These are like little people. So they also have life cycles. So that's why I love galaxies. Okay. And let's take a little turn and change topic and talk about space telescope. These are a few examples for space telescope that we have in the past. Webb is great, but without these space telescopes, we're not going to have Webb. These legacy telescopes or instruments are delivering science throughout the past decades to help us understand astrophysics, to motivate newer generations of observations. And of course, newer generations of telescopes as well. So Hubble is, of course, the one that we all know and love. But there's also Chandra that observe in X-ray, which is a totally different wavelength with observing of totally different phenomena. And then Spitzer is also great. It actually observed in near to mid-infrared. So it's very much like Webb, but it came like a decade before, or two, almost, actually 2 decades before. So that's what we had before we have Webb. And that is something we'll be comparing to in a few slides. And I also throw in a few ESA mission. So Herschel is also great for studying infrared, especially emission from dust. And then XMM Newton is great for UV and high energy phenomena. And then Gaia is, of course, the new generation mission that is great for studying stars. So stars in the galaxy is also very important. All right, you can do this. So there's so many things we can do. And these are just some examples I can tell you, but I can go on and on for an hour. But this is a Monday at 8:30, so I want to keep this light and fun, right? And I also just want to add that when Galileo first observed the moons of Jupiter, I don't think he would imagine that people will be flying crazy machines to it in less than 400 years of his time. So now we see the star next to us. I cannot imagine what happens in 1,000 years or less than 500 years. But maybe we will be there. Who knows? That's why we're looking now. Just like why Galileo was looking about a couple hundred years ago. So keep looking. We're going to keep looking. So let's talk a little bit about the history of the James Webb Space Telescope. It was the idea was first proposed back in 1989. Even before Hubble was launched. So for context, Hubble was launched in 1990. So at that time, astronomers and engineers already have the idea in their heads that they need the next generation space telescope. By the way, that's what James Webb was called originally, to look at the deep universe, to go beyond what we have with Hubble even before its launch. And this is one of the early design that came out of Goddard, actually. So if you go online and look for the early design of James Webb Space Telescope, you will also see the other ones from Lockheed Martin, from JPL. But this is the one that sort of kind of made it to the final, kind of. This is from, I think, 1990. But pretty close to what we look today. So I'm always amazed by the vision of people, the person who draw this or the people who came up with this, because they have some vision. This is, what pretty close to what we have today. And this is not what a telescope looked like at their time, okay? A telescope has tubes back in the days. Now they don't. All right, so this is what the blueprint illustration looks like. So Webb is full of moving parts and new technology. There are things that has to be invented while they build Webb. It's building on technology that doesn't even exist at the time. And because this telescope is so big, a lot of parts has to be folded up before we can put it into a rocket and launch it to space. That's why we need to test it so rigorously. Everything has to be tested. We got one shot. Hubble goes wrong, we can go fix it in the orbit. But if anything were to go wrong with Webb, there's no coming back. There's no planned mission, no money, no technology to go fix it. So it has to be right. That's why, there's a lot of testing has to be done, and the technology has to be mature over time. And just to say a few more words about its structure before I get into the images. No? Okay. So you can see the mirror is huge. Webb's iconic hexagonally shaped segmented mirror is the whole thing together is 6.5 meters across. There is a person next to it for scale. So this telescope is really, really big. And to the right, it shows you what it looks like when the mirror is folded up. There are 18 segments of the mirror, and they kind of function independently, can be adjusted independently. So they are folded up to make it smaller so we can put it inside a rocket head. And then on the bottom, there is an image with the sun shield on. Webb is an infrared telescope, and it has to be kept extremely cool. It has to be very, very cold so it doesn't observe itself. You and I, everything with the temperature emits in infrared, just in case you didn't know. So in order to avoid observing itself, it has to, have a sun shield to keep the whole thing cold. And we'll get into that a little bit. So the sun shield is about the size of a tennis court, and this thing is absolutely humongous, even though on ground, to the things that we see every day. So that's why this thing has to be folded up. And this is what it looks like. So I included these slides because it actually was very sentimental to me. So I've been working with Webb, I think not too long actually, for only the past 5 years. So there are people who definitely work on it longer than me, like Jim, like for over 20 years. But that was my whole scientific career here. And I've only seen Webb looks like that in animations. Whenever we show people how Webb will unfold, that's the first slide, or that is the first frame. When I see this happen, this is real. Webb is built. We're ready to go. All right, so that's the moment that it feels really real, like this is happening to me. And then on the bottom, that is the mobile clean room. So because Webb is very, very delicate and there's a very high requirement for how clean the air is that touches the telescope. We don't want any dust to cling onto the mirror because there's no way to clean them. So that's why when Webb is transported out to French Guiana, we have this mobile clean room, basically a suitcase made for Webb. So stick in there. Also feels very real to me. So it took a little while to ship it out to French Guiana. NASA was really concerned about all the security things, so they will never tell us where it is when it's in the sea. So we kind of know when it left California, and we know it's going to make its way to French Guiana. But we don't know what happened in between. There are some rumors, a lot of rumors actually. But finally, it arrived at French Guiana, and they have to install it on the telescope. And then there was still little small delays that happened afterward due to the weather there. But on Christmas Day last year, so not that long ago, December 25th, it was finally launched to space. That was an iconic morning, actually, 7:30 in the morning for New York, and I was with an observing team witnessing this, the final goodbye. We were told that once Webb is inside the rocket, we'll never see it again, and that's our final look. And this is not the animated version, but you know what happened next is that the solar array panel is deployed, just they come out like that. It's almost like he's waving goodbye to us. Anyway, it was so cute, that moment. So, but also I heard from my boss, who was the deputy project scientist at Goddard for Webb. He told me that is great. It happened earlier than they thought because there was almost no jiggle. The launch was so perfect. That's why the solar panel deployed early. So we're off to a very good start. And of course, that is thanks to ESA and Arianespace for the exceptional launch. And I think this is the perfect time to slip in. Webb is led by NASA, but also it is an international collaboration. We have people working on the Webb project all over the world. So this is just a very simple schematic map to show you where the people are. But indeed, it's a joint effort between NASA, the European Space Agency, ESA, which contributed the launch vehicle and several scientific instruments, and also the Canadian Space Agency, which contributed the fine guidance sensor and theorist. So yes, kudos to everyone, all the countries that help out. So after it was launched, it took 2 weeks for it to get to its designated orbit, L2. But also it took itself 31 days to unfold. Some people said that's 31 days of terror, because if one thing goes wrong, we lose a telescope. And I was the optimistic one. I kept telling people it's going to be 30 days of good news because all the system is going to check out, and we are going to get one good news after another good news, after another good news, after another good news. Well, my career depends on it, so I have to be optimistic. And we were right, everything checks out. We had a perfect deployment and everything works out. So that is just a sequence of how the telescope unfolds. Basically, the sun shield comes out first and it gets tensioned so it can start cooling off. The whole telescope operates at very, very low temperature, I think 50-something Kelvin for the whole thing, and then MIRI down to 6 Kelvin. So it needs to be cool, and that's part of the reason why it takes so long, because we have to wait for that to happen. We can't speed the process up. Okay, and this is where it went to. It is now. So Webb orbits around L2, unlike Hubble. Hubble orbits around the Earth, which is great. It's close to us. We can surface it. We can look at it. But Webb has to be there because it is way cooler out there. And also, Webb cannot look at the sun and the Earth. So that's the perfect point to put it there, so we can shield both of them at once. So the sun shield is facing the sun, and we'll look at the structure in the next slide, but basically the sun shield was going to block out all the radiation. I think the marketing term for that is an SPF of 1 million. So it's pretty good for blocking out the sun. And then to keep the other side of the sun shield, where in the instrument where the telescope is, very, very cool. It's a cool telescope, by the way. Okay, so this is what the telescope looks like in close. So the left shows you the basically the top side of the instruments, where the optical system is, where the scientific instruments are. Basically, everything that needs to be cooled is on that side. And then on the right is the sun-facing side, where all the hot stuff is. So the sun is obviously on that side, but also everything that generates heat, like the communication device, and then I think maybe the computer is also on that side. So everything that generates heat is kind of isolated on that side. So that side is actually pretty hot. but that's great. And just another closer look to the scientific instruments. So there are 4 of them. So basically, what happens is the light will bounce off the primary mirror, so the the hexagonal mirrors, and then off to the secondary, and then enter this chamber in the back, right? So all the light will be processed there by these 4 instruments. I think I can talk about them here a little bit. So the near-infrared camera, or NIRCam, says there, it functions like a camera. So it takes images of the universe in infrared, in near-infrared. And then the other one, NIRSpec, is a spectrograph. So it breaks down light into spectrum, or rainbows. So we can study the composition or the light signature of different elements depending on what we're looking at. And then next we have the nearest, which functions very much like a camera, except it also smudges the light, so we can efficiently obtain spectra for a lot of objects at the same time. So NIRSpec kind of works with fewer objects, but nearest works with many more objects. That's rule of thumb. But depending on how you want to use it. And MIRI is the cool one, well, literally. So it's the mid-infrared instrument. So because it's in mid-infrared, it's more sensitive to temperature. It has to be actively cooled down to 6 Kelvin. So it's really, 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 really cold. All right, so that's just the basics. And how do we talk to Webb? So whatever Webb sees, we have to be beamed back to Earth through the deep space network, and the signal will be transmitted through Goddard, actually, then to the Space Telescope Science Institute. So if you've never heard of them, this is a great institution. They operate the Hubble Space Telescope for decades, and now they're operating Webb, so the Space Telescope Science Institute. Great institution, great partner. All right, and this is what it looks like. This is the command center at Space Telescope in Baltimore, Maryland, actually. So they are now transitioning out to operation. So for the past couple of months, the space is occupied by mostly the commissioning teams, so people who monitor the instruments and calibrate them and understand them. But we're transitioning over to operation, which is more about scheduling observations. How do we use the telescope most efficiently? How often do we check on the mirror and see how they perform, that kind of thing. So more routine stuff. So this is the commissioning timeline. Hopefully this is not too boring. I promise you the nice images will come out very soon. Anyway, so we went through the launch and the unfolding and arriving at L2, the period. And then in the timeline of storytelling, we're somewhere in the middle of telescope commissioning. And this is also really cool. I want to show you. So when we first turn on Webb, this is what shows up. This is the image of 1 star, not 18. But because we just turned it on, so the 18 mirror segments are all doing its own thing. So when we take an image of the star, 18 different images show up. So what do? The first thing they do is they try to identify which image is corresponded to which segment. Is it showing up? So the lines are very faint, but you can see the wings are kind of circled in there. So we try to identify which image is corresponding to which segment. And then they have to line them up so that we know exactly which image is pointing to which, corresponding to which mirror segment. And then they can be adjusted individually. So every mirror segment has like 7 degrees of freedom. Can move up and down, left and right, front and back, but also they can tilt in all different axes. And then the curvature of each mirror can also be individually adjusted. So the proper way to say it is actually Webb is only half assembled on Earth. The other half is in space. So all the moving parts, because we know Webb will undergo a very violent launch. There's no point to fix anything. And plus, Webb is going to be in space for 15 years. So we have to be able to calibrate it. So this is why. And that's also part of the technological marvel. So they use a technique called wavefront sensing, and that's the dark magic that makes it work, like 1 mirror. Look, it's really hard. We have 18 mirrors here, all doing different things. And in fact, they all have different characteristics. That's why they have to be understood at first, and then now adjusted so they function as 1 mirror. But I promise you, the end result is stunning. So when they stack the 18 images and have them phase coherently, this is what comes out. So just a point spread function. But then on March, I think 11th or something, they released this image. It's just an engineering image made with one filter. So you can take this as a black and white image, except they use orange instead of white because it's infrared. Want to make sure you associate to that image. Already very breathtaking, actually, to me. So I tweeted, don't mind the star. Look at the galaxies in the background. In fact, Webb is so sensitive that we know every image that Webb takes will be photobombed by a galaxy because they're everywhere. And you probably get this from the first half of my talk. I'm a galaxy guy. So there it is. So here's some comparison. Again, these are just the pre-science engineering images that they periodically put out there to tease us. But on the left is a comparison between Webb and Spitzer. You can see there's no going back already. It's so clear. What have we been looking at for the past couple of decades? Now I see things. On the right is for mid-infrared. We went from WISE, which is a space-based mission, and then to Spitzer, to Webb. Again, there's no going back. How am I supposed to do astronomy anymore with these old telescopes? Anyway, but this is really stunning, even though they are not for science. These are just engineering images. All right, here comes the big reveal. Just kidding. Nope. Hold on. I show you these two on purpose. When I show you the image of the Earth and galaxy, were you stunned, to be honest? Not really, right? Because we know what the Earth looks like. We know what the galaxy looks like. I embarrassingly was born in the era that has Hubble. I was born after Hubble is launched. So I grew up in a world that we have images of the Earth. We know what the Earth looks like. We have maps. And then we know what the galaxy looks like. Even literally on top, is your wallpaper for everything. But remember this, there will be kids born after this week, after today, and they will grow up in a world with Webb images. And you, like me, witness this transition, just like I show you. What have we been looking at in the past? This is what we have now. There's no going back. The world has progressed. All right, so I'm done messing with you. This is the big reveal. All right. Just kidding, not done. So that's Hubble, by the way. This is how you can tell. If you see 4 spikes out of a star, it's Hubble. This is due to the optical design. If you see 4 spikes out of a star, it's Hubble. So let me do some transitioning. I think this is the only way to do it right. Okay. Whoopsie, spoiler. Okay, so there is the same field. This is a massive galaxy cluster you're looking at. Let me do the explanation first. So in the center, there is a massive galaxy cluster that has the mass of about 300 trillion solar mass. What is that? So 3 with 14 zeros after it, multiply the mass of the sun. It's a group of galaxies. Very, very massive. It's so massive that it bends the field around it. So we can see galaxies from behind with the light go through the area that is banded. And then the area functions like a lens, and then it comes to us. So gravitational lensing. And that's one technique that allows us to see further back into the sky. I tell you all this, but you can't see. And now you can. Gotta do this right. So you see the features out here. Let me just use my pointer. These lenses, there are so many of them. There's actually already 2 papers out there identifying the pairs and the objects. So this is the fun thing that happens whenever a light source is banned by, go through a lens. It gives rise to multiple images of the same object. So if you look at them, they will have the same signature, spectroscopically or photometrically, meaning color or rainbow, but same. But if it's from the same object, they probably look the same. So there are groups out there already going after these different pairs. Why is this important? Because this helps us understand the mass distribution of that cluster. And by understanding that really well, we can use model to reconstruct these lensed band galaxies. Why is it important? Because this lens helps us go further out, go much further out, and it magnifies the sources behind it. So this is one of the reasons why it is called the Webb's first deep field. This is a very deep image that's taken by Webb, but also with the lensing, it's going deeper, maybe even deeper than the Hubble ultra deep field. The fun part that I forgot to say actually. The Hubble Ultra Deep Field, the objects that we have been playing around looking at, it took about 22 days to image, 22 days worth of exposure time. And that took about 50 days to complete the process. That's why we only have one. We can afford to do another one. We have to find a good reason to do it, and there hasn't been one yet. How long did it take? It sounds like a salesperson. 12 hours. That's all it takes now. 12 hours to get there. What's going to happen if I have 132 hours to spend on it? I mean, we do, but we'll let you know in December. But again, the theme for today's talk really is about zooming, so I'm just going to zoom. This is what we had in the past, though. I mean, not disappointing. Hubble is great, and Hubble took this image with only 5 orbits, so that's about a couple 100 minutes. But with Webb, again, there's no going back. We can see everything now, so clear. Look at all those little details, those features. Galaxy with a spiral arm. This guy down here, this guy. Look at what we had before. Well, we still see the galaxy, but there's a lot of guessing and doubt in there. Like, what is its property? Do we know how much gas is in there? Do we know what its history was? What about its metal content? Well, now with Webb, it just becomes so easy. I shouldn't say that because the observers would disagree with me. Still a lot of hard work to make that happen. But I'm just saying that we can actually now do a lot of these things with much better confidence. We can see now. And I don't know, I still encourage you to just grab the image and do what I do. Just go around and do some sightseeing. It's a pretty nice field. So this, I think Colin made it, I'm not sure, but it's just webcompare.com. So really handy tool, runs really great on Chrome. Don't do it on Safari, but just do back and forth a bunch of times. This is the proper way to savor this image. Okay, with the comparison back and forth. All right, let's move on to the next one. Carina Nebula. Again, I have Hubble on top first, so we can talk about things without spoiling everything. So this is sometimes referred to as a rift or a cliff of cosmic landscape, because it looks like one, but there's no solid ground for it to stand on. What's really going on is that there is a star that is outside of the frame on top, way up there. So there's radiation coming out of that, that star that pushes the gas downward or outward in general. So the blue is where the radiation goes through, and then that sharp cliff is where it kind of stops. So sort of where, well, the shoreline or the cliff is still moving at 24 kilometers per second. It's really fast. But in the cosmic scale of things, that is basically static. But what's really interesting about this is we know stars form in very dusty region because stars need material to form. And if we look at this with mid-infrared, we're penetrating through a lot of those gas. And of course, this is stunning to look at. Again, all the points with 6 spikes, these are stars sticking with Webb, 6 spikes because of the hexagonally shaped mirror. But what you're looking at here has a very, very cute description for it. It's a baby star nursery, or baby stellar nursery. Stars forming actively in this region. It's a nursery for little stars to form. We're looking into the first stage and trying to understand how that happened. And why does that matter to you? Because you are made out of stardust, all of you. In case you haven't heard about that. So all the heavy elements are made inside stars. And then when a star explodes, it's got distributed across the galaxy. And then somehow the next generation of star forms. It goes into the planet, goes into you. So you literally are made out of stuff that came out of the center of the star. And those stars came out of regions like this. That's the connection there. All right. Again, I don't know. You probably want to do some zooms. I will do that. I'm just amazed how high resolution this is. Like, TV, YouTube doesn't really do justice to this kind of detail. You have to do it yourself. You have to go do the zoom, pan it around. You cannot do this in one pass. You have to, just like going through a park, you have to do the sightseeing yourself and try to look at every little detail and see what is going on in there. All right, here's another one, Steeping Quintet. In a very small region, there are 5 galaxies in pretty much the same patch of the sky. So this is actually a bigger region. is made out of about 1,000 snapshots of James Webb. So James Webb has a very small field of view. So in order to take image of a big object or cluster of objects like this, we have to do a mosaic. We have to stitch them together. So let me explain what is going on in here first. There are 5 galaxies. As you can see, the 5 bright spots. The one on the left is actually 10 times closer to us than the other 4. That is a foreground object. It doesn't know the other 4 galaxies. We saw them together somehow. And then the other 4 are actually physically bounded by gravity. They're interacting with each other over maybe a couple billion years. They will merge together. So in a system like this, it's really important. It helps us understand how galaxies interact with each other. A lot of crazy things happen when they spiral around each other. There is like a phenomenon called tidal stripping. So when part of a galaxy gets close to its companion, and then part gets stripped out, and then when they start merging, some of the stars get flung out, that kind of thing. All right, so physics. But the detail that we get out of it is gorgeous. It's not just that, but also there are features that wasn't really seen before. For example, this trail of gas. I mean, we know galaxies do this kind of thing when they merge, but in the past, we're not even sure if it's connected. I mean, we see traces of it out there, but we don't really see if it's connected as a trail. But here we have it. We have the full picture, and with the mid-infrared capability, we can see some of the hot gas content in there. So not just the stars, but we can also see what the gas is doing. All right, here comes another one. The Southern Ring Nebula. So this is kind of like the Carina that we saw before, but this is a bigger region. So what is going on here is that we are witnessing the sight of a dead star. So our sun would do similar things in 5 billion years later. So not to worry about it yet. But this is one type of ending for stars come to the end of their life. There's a white dwarf that left in the center. Don't mistake that for the bright spot. It's actually a living star. So what's going on in there is a binary system, which one star is still living, the other one just died. And then the shell is the left. What you're looking at is the left behind material. Some of the hot gas, some dust, a lot of dust actually. Also metal, a lot of heavy elements are in there. That's why it gives rise to this kind of color. So in the past, we see that this region is kind of smooth and nice. Okay, I'm just going to give you the whole thing. Now we see everything. We see layers, we see structures, we even see, well, come on, you can do the zoom. Background galaxies. Yes, as I told you, every picture will be photobombed by a galaxy. So when this first came out, the guy wasn't sure whether this is a feature of the nebula or if it's a background galaxy. And later on, they realized it's a background galaxy that is edge on. So you're looking at the galactic disk facing you with the bulge in the center. You can see there's a bulge. But this is the kind of problem we're dealing with now. Background contamination. We just, have things from the background that randomly pop up. So not a bad thing for me. But this is gorgeous. All right, let me go back to my talk. I'm not done yet. Nope. Okay. So the last image I showed you was in near infrared. And what I'm showing you on the right is in mid-infrared. So mid-infrared is better at penetrating through dust. And now we can see the companion white dwarf. So you can see in the middle there is the star that shows up in the left. This is a perfectly healthy living star, just like our sun. The left is what left behind when a star go into a nebulae. So this is a white dwarf, basically the core of a star that get left behind. It's still really, really hot. That's why we can see it. So combining near infrared and mid infrared, we just see so much more things. Like, this is why. Okay, so this is spectra. I mean, they're not as visually stunning, but scientifically, this is really, 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 really important. So I know I talk about galaxy all night. I won't shut up about it. But also, there's another very important field of study, and that is planetary science and exoplanets. So there are planets orbiting around other stars. And for a long time, we cannot study what is in the atmosphere of those planets. So now, with Webb, a sensitive instrument like this, we can actually see starlight that went through the atmosphere of the planet that went in front of it and enter the telescope. So this is a spectra of it. So basically, we break down the light to see what is in there, to see its composition. And surprisingly, it detects a lot of water vapor in the atmosphere. So this is great. I mean, this is the kind of tool we have, and we'll be able to understand so much more about exoplanets than we currently can. We just passed the mark of detecting the 5,000th exoplanets, and more will come in the future. All right. So that was the 5 images that came up with NASA. Do you want more? Right? Because you have seen these 5 already. I mean, I probably do a better job explaining them, but you probably want more. So I work with teams, and well, I grab a lot of these from Twitter, so you can too. But anyway, I'm here to do the explanation. So this is one of the teams I'm on. It's called the Cosmic Evolution Early Release Science Team. It's a mouthful, so we just call it SEERS. We are one of the teams that actually have received data from JWST. Our data was taken in June, but it was embargoed until now. We now know why, right? Because if we get the data early, we'll reduce all the data and put out images before NASA does. No one should do that. Anyway, so this is what we got last Wednesday. And on the left is Webb, on the right is Hubble. Not that impressive. This is the first look. What is really impressive is that the left image is just 1 out of 650 we have. This is one snapshot. And that's Hubble with how much time? Anyway, so that exposure on the left took only 1/4 of the time than is spent on by Hubble. So this is just to show you, this is just the beginning. Everything you saw today, the 5 images from NASA, was just the beginning. We are entering a new era of space exploration, of understanding the universe. All right, there's more. So that was July 14. So last week, right after we got the data. This is a colored image already reduced from 3 of the bands in one of the near-cams or near-infrared camera pointing. We can really see a bunch of galaxies in some preliminary colors. And some of these galaxies are really far away. This is just like the Hubble Ultra Deep Field. So there's no star in the foreground. We're just looking at galaxies at the utmost distance. So that's why they look like blobs, because some of the galaxies are really, really far away. But maybe we'll find the first one in there, like one of the first galaxies formed in the universe. And if we zoom in and tune the color a little bit, you can see a comparison between Webb and Hubble. I mean, we see absolutely more detail. Again, these are really distant galaxies. These are not vanilla. This is not cherry-picked. These are really, really far away and hard to study galaxies. So with Hubble, in the past, it looked like blobs. Now we have some detail and structure. But look at these galaxies up here that didn't even show up in the Hubble image, or just have a point. This is what I mean by we always have doubt when we try to study these galaxies. Are they noise? Are they detection? Are they sources? Are they contamination from the foreground? Hard to tell. Now we kind of know for sure that this guy has structure. It's probably a galaxy. And then these are still blobs. Maybe they are just something else. Again, this is super preliminary. It's on Twitter, so I can show it to you, but this is just the beginning. This is another example to show you a composite color image. I think on the web is Hubble. In the past, now we see a lot more structure. And, probably the gas in between the two. Oh, these are stars, actually. All right, so this is just one team. This is another one, planet. So this didn't make it into the 5 first images, but this is actually in the document that they evaluate the performance of Webb. By the way, Webb is performing surpassing expectancy for like a lot. It's performing so well. So we're going to I think some of us are joking how the people who got time this year are, has an advantage because Webb is performing better than we think. So we are going to get more galaxies out of the time we propose. I'm sure they will correct for that in the future cycles, but we have an advantage for going into cycle 1. But this is Jupiter with Europa next to it. And it just looks gorgeous. And this is another one from the FANG's group. So FANG is physics at high angular resolution in nearby galaxies. So again, astronomers like to name their surveys. So this is what they name it. What happens on the left is a galaxy nearby. You can see the structure resolved, very nice, very clean. On the right, though, with Webb, what are we looking at is tracks of, I think, dust. So this was a feature that was recently noticed, that there are a lot of things going on in galaxy. Apparently, there are channels that are more efficient for dust to pass through. So these are like highway for dust inside a galaxy, inside a spiral galaxy. Isn't that cool? The kind of detail that we can learn from these observations just by looking. We don't even have to go there. All right, we also get art inspired by James Webb already, which is very, very nice actually, except this is not Starry Night anymore, this is Galaxy Night. A lot of galaxies in the sky, which is so great. And also we get memes, a lot of memes. I know, right? And this is a good sign. These images are so stunning that everyone loves them. No one even asked me about anything else, just how do we make them, the images. And then, yep, I actually still got a few more to go, but you share my joy. Hubble on the right, James Webb on the left. You all seen this meme before. And now we see things with the glasses on. We hope it's that easy. And then, of course, the day after the images come out, we log onto Twitter. That's what happens. Everything you see is a Webb image on the news, on Facebook, everywhere. But it's a good thing. So I'm really grateful for how it turns out and how supportive the public is. I really hope that this will be the inspiration for a new generation of astronomers and also for a new generation of great scientific instruments. This is now the gold standard, I guess, the milestone, but this is not the ceiling. At some point, we'll go through it. All right, so stay excited. Just remember what these are and keep zooming. Questions?
Hello, thank you very much. Really awesome. I wanted to ask, is the color of the images affected because of the gold on the mirror? Because even though it's not visible light, the way that we see the images of the mirror, obviously we do see the gold. So is the color affected by that?
Right, so very good question. Gold is chosen because it's the best material to reflect infrared light. So it doesn't do much on affecting the color, but thank you for the question. I really have to point out that our eyes do not see infrared. So I was once joking about how NASA will release the first infrared images. It's just by showing you a black image, all black, and tell you that's an image from James Webb, because that is true. We don't see this color. So there are two very common techniques. I think most of it was used here is just transposing. So we pick a few filters, just like how our eyes work. So we have the longer wavelength infrared represented by red, the medium wavelength infrared represented by green, and then the shortest wavelength infrared represented by blue. And then we do this composite color. So the color is still true to the wavelength range, but shifted to or transposed to a range that we can see. But I also want to highlight that there's another technique called false coloring. So that is more common when we try to show multiple things inside one image. In the past, we have taken very detailed image of a galaxy, which we try to show you the hot gas, the cold gas, the stars, the metal, and even for the bullet cluster, we try to show you the mass. So we try to show you multiple things in one images. Then that time we try to identify what the things are, and then we give the distinct colors so you can visually tell them apart. So these are the two coloring techniques. But I think this was pretty true. I should just go back anyway. Yep. Thank you for the question.
Hi, thanks for the presentation. I have two questions. One is related to the spacecraft. So I was wondering, the thermal protection shield is quite complex. And I was wondering if you could use Earth shade and use nuclear power to power up the spacecraft, and this would be a viable design, or will be an impossible solution in some way. First question. Second one is related to the distortion of light we are seeing in some photos. This is totally explained by Einstein's explanation that the gravity field will distort light, or it just changes the position in space of the source of the light.
So let's get to your first one first. So while it's on the other side so we can shield the Earth, I don't think we're shielding the sun completely, because we still need to get solar power through the panel. And then I don't think there's a lot more I can say about that, because I don't actually work on the hardware. I'm not sure if I can answer the second one actually, but we can talk afterwards. You know.
I was also wondering about the shielding. You said it's big, so can it act as a sail, a solar sail, and is it a challenge? And the second question is, what's the amount of data coming out of James Webb?
Right. So I can answer the second one first. So I just looked it up today. Actually, I have it included in one of my earlier slides. I didn't speak out, but I think the downlink is about 50 gigabyte a day, which doesn't sound like a lot, but it's really far away. And the transfer rate, I think, is about 28 megabits per second, something like that. So it's pretty fast, actually. It's like broadband internet. Except, for those of the images you see, they are made up with multiple, actually very many snapshots that has to be sent back. And those are, what is being sent back is the raw data. So we have pixel data per filter for every snapshot. And then they just all have to be sent back to Earth first before they can be processed. So I don't think the transfer speed is bottlenecking any of the science, but we're basically at the limit where how much ever images we take with Webb can be sent back, but that's pretty much it. Yep. And I'll get to your first question maybe afterwards. Yep. Okay.
Yeah. Hi. Great presentation. Hello.
Hey.
Just referring to the picture for the exoplanet. My question is, how small can we go? I mean, can we maybe detect gases of a Earth-sized planet? Can we find some alien friends to talk to?
That is a good question. I think it depends on more about the size of the planet, especially when we're talking about it passing through the atmosphere. So would it even show up in the spectra? It depends on how thick the atmosphere is and is what is in there. So I think that's pretty much all I can say. Yeah, again, I'm a galaxy guy, so I'm still learning about all this exoplanet stuff.
Hi.
Hi.
As a galaxy guy, I have two questions to you regarding galaxies. First, you and everybody else mentions that we see very, very, very far away galaxies. So my question is, what is the limiting factor? Is it the wavelength? Is it the color light collecting ability? Or is it like we really might be seeing the very first galaxies in this universe?
Very good question. So that's right up my alley. So it depends on a few things. For example, how bright the galaxies are, and also actually how prevalent they are. So I make predictions for how, not exactly where the galaxies are, but the predicted number density of they are. So for example, if I surveyed yay big of the sky, how many galaxies do we expect? But as we go to earlier and earlier times, at very close to the Big Bang, there isn't quite enough time for galaxies to form. So even though we have the potential to detect light from there, we might not be landing our sight light on a galaxy. So Webb has a relatively small field of view, so we cannot do large area search. But that's why the simulation becomes so important. We have to constantly balance. Do we spend more time on surveying a bigger area? Or do we go deeper and deeper and deeper in space, try to find something really, really faint? But again, it all depends on what the survey is trying to do, and there's no one rule fits all. So we keep trying.
And small follow-up question.
Yep.
As a galaxy guy again, is there some particular galaxy or galaxy cluster or something that you're particularly waiting for Webb to image?
Good question. Jim knows my problem. I have always been looking too far, so I don't actually know the nearby nice galaxy. But I really want to see that we go deeper than the ultra deep field. I really want to see another image that that rich, full of crowded galaxies, so I can zoom in as much as possible and get all the gorgeous details. So I guess it's not for a particular galaxy. I just want to see a deep field. That's my passion.
Thank you.
We have a question online from Erin Robot Girl. She's asking you, what other information can we gather from various light signatures? Could anything not yet known be found in the data? Thank you.
Let's try and see if I understand that question. So what can we get from the light signature? Well, this is the only way we interact with the universe. Well, now with maybe gravitational wave is another channel, but we interact with the universe passively through observations, and there are a lot of lights coming toward us. But by interrogating really, really hard, we can extract a lot of physics out of it. So that's the goal, what we're trying to do. I said earlier that maybe with Webb it's easier. It's actually not, because Webb is showing us a lot more things now. That just means that we have a lot more interrogation to do and a lot more to extract from the universe.
Hi, I have a question. This is an uneducated question, but would the James Webb Telescope be able to help us see the black holes in the centers of galaxies? Or has any telescope done that, or can we even?
Right, thank you for the question. So direct imaging is done with the Event Horizon Telescope with a very different technique. So James Webb only observed in infrared, so we are not going to be able to see the black holes themselves. But as you may already know, black holes in the center of galaxies, these supermassive black holes, accrete matter very quickly, and they produce radiation in the process. So a very interesting phenomenon is that because they have their accrete matter, so they often cover or wrapped by dust and gas. So a lot of these active galactic nuclei, or sometimes known as quasars, are actually obscured. So one thing really cool I think our team and many other teams will do is actually use Webb to search for these obscured AGN, obscured black holes. So we cannot really just study the naked black hole by itself most of the time because how covered they are, but through how they interact with their nearby matters, how they accrete things, we can still understand how a black hole works and know that it exists. Thank you for the question.
Oh, hiya. This may be a bit of a silly question, but bear with me. I just wanted to clarify something you said earlier.
Yep.
You were talking about the mirrors having 7 degrees of freedom, and then you said we can adjust the curvature. Did you mean we can adjust the curvature of the individual mirrors, or only collectively by angling them?
Individual mirrors, actually. So I heard this from an optical engineer also at NASA Goddard. So there are actuators at the back of the mirror that actually, go tighter or looser to adjust individual mirrors' curvature. So it's individually adjustable. And this is really important because some of you might have heard that there was a micrometeoroid impact on the mirror earlier, a couple of weeks ago, a month ago. So this actually is expected to occur over and over again throughout Webb's lifespan, and it is expected that the mirror performance will degrade over time. But because of how the mirror is engineered, this gives us the freedom to actually sometimes just cancel out those effects. So the mirror is actually being constantly monitored as part of operating a telescope. And then they are constantly adjusted, I think, once every few weeks so that it's always in its best performance.
Oh, great. Thank you.
Thank you.
Thank you so much for this talk and your enthusiasm. I bet the James Webb Telescope is very popular right now and is fully booked for the upcoming years, maybe even. As someone who is in the know, which I assume you are, is there a particular experiment test slot that you're particularly looking forward to that is already planned?
Right, there are several. So in observations, we call these programs. So there are the next year of JWST's operation is already scheduled and is planned. So I would just say a few. So Sears is the first one that will put their data out publicly. So everyone can just grab the raw data and do whatever they want with it. Maybe they will find something that our team don't and scoop us, which is totally fine. I say that, but my teammates might disagree. Hope they're not watching this. Okay, but there are also so many other things that Webb will be doing in the future. For example, there's a program called NGDeep, the Next Generation Deep Extragalactic Exploratory Public Survey, which was awarded 130-something hours to go back to the Hubble Ultra Deep Field. That this time we're going to obtain spectra for a lot of the objects, but also image the field next to it. Extreme depth. So this will happen the end of this year. So just wait, maybe early next year in January, February, you will see a new generation of deep field. I think NASA worded very clearly when they put out the Webb's first deep field. They said this is the deepest image of the universe, at least for a short period of time. Because they have 12 hours. The engineers don't get all the time they want. But when it's now in full science operation, and we can go deeper and deeper over the years. Maybe in 5 years we'll get 500-hour exposure time on something. Who knows? So that's one thing. But also we want to be able to use Webb to study the large-scale structure. Galaxies are fun individually, but we can also get a lot by studying large areas. There's this cosmic web structure because the matter in the universe collapse under gravity. They are not randomly distributed, so they naturally fall into filaments of matter, including baryonic matter and dark matter. So by studying a large area of the sky, we can get a glimpse of what this structure looks like. We may see a bunch of galaxies that lies inside a stream, but we also will find regions that are, this huge void that has absolutely nothing in there, no galaxy, no gas. So a lot of exciting things will happen next year. Of course, Jim is looking forward to a lot of exoplanet program and also planetary science program. Well, there's a good friend, Heidi Hamill, has a GTO program, a Guaranteed Time Observers program, which has about 100 hours to look at all the outer solar system planets, which is great. So look forward to that too. Yep.
And we have another question from online, from Neve Show. Aaron, you're awesome. Thank you so much.
Thank you.
She's saying that. What big question about our universe would Aaron like answered from Webb?
Wait, what?
Sorry. What big question about our universe would you like?
Would like? Okay, now I get it.
Webb's answered. Yeah, thank you.
So there are these really big questions that all of us are trying to understand. So how did it start? How did we get here? In terms of all the physics that happened in the past, how our own really massive galaxies formed, and then how do we get these galaxies that we live in today? This is probably the reason why we study cosmic history. But also in general, how does the universe work? How does physics work? Does the universe expand at all? It does, but how fast? And then, why is it expanding? There's so many questions that we want answer to, but just down to the basics. How do we get here? And how does the universe work?
Hey Aaron, I wanted to ask how much of the observable universe are we able to see in detail now?
Right, I need to do a backup envelope calculation. So actually a lot. So let me throw some numbers out there. The universe's history is about 13.8 billion light years. That is calculated from the expansion rate of the universe. So we figure when it all started. So I think the current record holder of the most distant galaxy is about 13.6 billion light years away. That means it was forming just 200, or maybe a little more than that, maybe more like 500. So 500 million light years after the Big Bang. So we're going back to, let's say, the first 5 to 7% of the cosmic's history. Again, this number might not be accurate, but throughout the really long cosmic history, we're going back to the first few percent, which is very impressive already, I think. All right. Are you guys tired?
I'm on my way.
It's almost 10.
Okay, not sure if I will make sense, but what's the interest behind the red blotches that looks like two merging suns or galaxies?
You referring to the Stephan's quintet? Wait, no, too far. That's a different one. So let me try to share those images again, just in case I get questions about them. Is this what you're referring to?
Yeah, I think so. The one.
There are only 5 images. So what was your question again?
What's the interest behind the
right? So in galaxy formation theory, at least, we think galaxies grow, change characteristic, or get its mass a lot of times through merger. I mean, when a galaxy sits inside the universe, it constantly gets an inflow of hot gas from the universe itself, because the universe has some gas in it. But for galaxies to grow in mass, especially grow stars, it has to go through merger. When two galaxies merge, it creates this influx of hot gas when the galaxies come together, and then it also drive up the pressure a little bit, which will make star formation more efficient. So that's why we want to study merger. Actually, a lot of people in my team are going to use Webb images to try to look for merger events and try to reconstruct what the progenitors or the merging parties are like.
Hi, thank you for your presentation again. So I'm a teacher in Colombia, so my question might be related with an educated question. Have the James Webb Telescope have programs like the Hubble Space Telescope had, like volunteer program for a student in American countries?
So the question is, can students use the telescope?
Yes, like the Hubble Space Telescope, I knew they have a volunteer program from international students.
Oh, interesting. So I know the two telescope operates in very similar way. So the part that I know is that all the programs, almost nearly all the programs, are solicited from the community. So astronomers has to write up proposals to justify their science to get science time. So maybe there are direct or discretionary time that give extra opportunity for students who wants to use it. But I'm actually not sure about how Webb will handle that. But worth checking, actually. Yes.
Hi, hello. I wonder what will be an event that will make a delay in the schedule that you want to point suddenly the telescope at, like supernova or a comet passing.
So there are actually, yes, time-sensitive events happens all the time. And speaking with one of our colleagues who does supernova physics, I think they have a limited number of times that they can pull that trigger to move the telescope to screw up everyone's program to look at their object, which is fine. But one thing tricky about Webb is that it has a very limited field of regard. So the field of view is what you can look at a time, but the field of regard is the field that Webb is able to see at that particular time period where it is at. So Webb, let's say this is the sun. Webb has its sun shield facing the sun that way, and the telescope is out here, right? The tower is out here. But the telescope can only point in this direction, but not quite that direction. So the field of regard looks like this the whole time as it goes around the sun. We have this donut or tire look-alike shape that goes around the globe all the time. So with this design, we can still survey the whole sky throughout the year. But when a time-sensitive event pops up, it might not fall within Webb's field of regard, and therefore we cannot do anything about it. Yep, but that's just life that they have to deal with. Right.
I was wondering now if I think it's the large array telescope. If there's any plans to coordinate looking at the sky, like with the large array telescope, James Webb, like
yes,
throw everything we have at looking at the sky at one point to see if there's anything of interest there.
That's a really good question. So I have to say, sometimes we say that Webb is the successor of Hubble. It actually is not. It is the successor of Hubble in one department, that is searching for extremely distant galaxies, because that is what Webb is built for. But for example, Hubble has the capability of observing in UV and optical light. Webb cannot do that. So, and Hubble is going great. We have no plans for retiring Hubble. So we actually are capitalizing on the fact that we have both flying in the sky, operating extremely healthy, and astronomers can propose to use both telescopes in one program. So there's this joint observing program. If you can justify your science that you need both UV and infrared and mid-infrared, then yes, you will get time on both telescopes. Who knows what that's going to reveal. So that is possible.
Hi. We've seen that James Webb can look at objects really, really far away, really awesome resolution. Are there plans, and is it possible for James Webb to look at relatively close by objects?
Yes, it can. And thanks to this man in this room. So I guess Jim can tell the story too, but Webb at one point in its development have lost its capability to look at planets, because planets move really fast relative to the background galaxies. So Jim, as a planetary scientist, head of planetary at the time, said this is not acceptable. How? This is the best telescope we ever built. If that cannot look at our planet, that's not going to happen. So he found the money. How much was it? $2 million? 12, sorry about that, off by 10. He found $12 million, and the engineer made the necessary adjustment, and it can actually track everything that is on Mars orbit onward. So we can use James Webb to see Mars really close by, and then we can also use that to track asteroids and then also the outer solar system planets. Actually, we have a program for that, so look forward to that. Maybe images will come out in the next few months.
Hello. Yeah, thank you for the interesting talk. My questions are more related to the engineering of the telescope rather than the science. So
I can
hope
try,
can
but
answer.
you know.
Yeah. Okay. I have two questions. First question is regarding the intricate disassembling, unfolding protocol mechanisms. Wouldn't have been. Now we know it worked, so everything is fine. But wouldn't have been more prudent to put it in a lower orbit? This unfolding it in Leo. And then if everything goes all right, we don't need to send astronauts to fix it or something. Then we send it to L2. That's the first question. Second question is I heard it has been designed to allow robotic refueling. Is that correct?
Multiple what?
Refueling.
Oh,
Autonomous
no.
Refueling.
That's definitely no. So there was never a plan for refueling. Yes, that was the plan. That was the plan. So let me answer your first question, and only from my own understanding, not representing NASA here. So there are several technical challenges. For example, we don't have the space shuttle anymore. It's actually hard to surface things in orbit these days. Not even a satellite can be surfaced. So it's difficult. And well, with that said, I think it's probably cheaper and more practical to just get it in one go. But I also want to highlight that there are actually contingency plans. For example, what if one of the mirror doesn't work? We actually have plans for that. We have a lot of plans for that. There's a scary document, that describes how James Webb works, and there's this 300-something point, single point failure. If one of that happens, then we lose the telescope. It's really scary to read through. But basically, what it says is, if one mirror stops working, we just point it away. If a side doesn't deploy at all, we just lose some of the reflection, light collecting ability. But we'll still have a telescope. And then if both sides don't deploy, we will still have a telescope because the primary is there. What was really scary is the secondary mirror. If it doesn't come down, then we don't have a telescope. So when that came down, everyone in the astronomy community is like, yes, we have a telescope. So that's the first thing that came down first before the side comes out. But once that comes down, we have some confidence that, yes, we have a telescope. But again, there are also, I think, 40-something single-point failure that will be there for the rest of Webb's lifetime. For example, if there's a huge piece of rock just goes right into Webb's mirror and then, just smash it somehow, then we won't have a telescope. So these are scenarios that we have imagined that will happen, and it's written on the book. So we prepare for that. But they're likely to be there throughout Webb's lifetime. Yeah, but I can talk a little more about the end of mission plan. I learned that from Jim. So if we runs out of fuel, which is actually not the most concerning issue anymore because the launch was so perfect. I think we have enough fuel for at least 15 years of operation. That doesn't mean we will have that because there are still the other risk factors that will still remain there for that whole time. But let's say at the end of JWST's life, if it's go out of fuel, we probably would just have it turn on and let it keep collecting data, but have it drift away. But if one of you here come up with a smart plan to tow it back, please do that. Well, I guess it would be really hard to tow it back, but also surface it in the station. But who knows what we'll have in 15 years? I mean, yeah, so. Yeah, anything can happen. Maybe start thinking about it. Counting on you.
Hi, me again. So I have a question with regards to, you kind of answered it because my question was actually, what are the biggest threats to the Webb telescope, and how far can it, be broken until it's no longer usable, and what happens actually if the James Webb telescope is no longer functioning in 2 years? Is there another telescope already in the plans?
I'll cry. That's what's going to happen.
And my second question is actually, what could Webb discover? As in, what are the goals of Webb besides deep space imaging, and potentially what could we discover? Because I feel like we covered everything except for what is actually the purpose of Webb.
Right, yes. So let me get the risk part first. That's easy. So there's so many of them, but I'll just tell you two. So if the sun shield rips and then we lose a layer or two, then we'll have hard time to keep the science instrument cool, and that will significantly degrade our ability to detect infrared. So that's one big risk factor. The other one is actually MIRI. So the mid-infrared instrument has to be actively cooled because it has to, it's sensitive to temperature. So it has an onboard cryogenic cooler on it. So if that stopped working, then MIRI won't be at its working temperature, and therefore it won't be working. So that's one of the other things that I see could fail. And Webb's mission, I am responsible for making you think that Webb only look deep, because that's my passion, that's what I want Webb for. But Webb is actually a versatile telescope. When you look at, I encourage everyone to go Google James Webb Space Telescope Cycle 1 selected programs, and they have so many categories. It's going to do solar system, it's going to do exoplanets, it's going to do galaxy, it's going to do large-scale structure. It's also going to study supernova and all sort of things. So everything you can name in astrophysics, astrophysics has so many subfields. It pretty much is going to do all of them. So yeah. And again, this is one of the talking points I had when I was lobbying at Congress for a different cause. But what was so great about Hubble is the part that we don't know about the universe. When they first took the Hubble deep field, not even the ultra deep field I showed you today, back in 1995, they took the first Hubble deep field. A bunch of galaxies showed up, and the world freaks out. We weren't expecting that. Someone came up with the idea, let's image a blank piece of the sky for an extended amount of time, and then that came out. So with Webb, the best part is the part that we don't yet know. I've spent years making predictions for Webb. I didn't say that, but when I saw the first Webb images come out, when I see the real universe imaged by Webb, it was very sentimental to me. But imagine what we can do with Webb over the years when we try to tap into the unknown. Maybe we find a Tesla out there. I'm just kidding. No Tesla. But the part that you don't fully understand and the part that surprises you is the best part.
All right, I think this is the end of the questions. So thank you very much, Dr. Young. It was really spectacular. Sometimes I think, when you think you in a historical moment, you are somewhere. I think from, now, like 5, 10, 15, 20 years later, when we look back today, we will say, I remember where I was when the first Webb images came from, and it was during SSB. So, it will be really historical for us, and we will also remember this particular event and saying that we listened to Dr. Aaron Young and telling us the first 5 images and what's next. So thank you very much for joining us.
Thank you. Thank you, everyone. Should I walk up the stage? All right. I don't want to cause a mess, but if you asked a question earlier, we got posters. I only got 9 of them. Don't rush. I'm sure you want them, but make your way here. First come, first serve. No running.